I'm Ting Wang from National Taiwan University. Today I'm going to talk about an extinction-free agent census by 23 space-based infrared band activity. So here I want to introduce what AGN is first. AGN is active galactic nucleus. This is a compact region at the center of the galaxy that is ultra-luminous. And why it's important for us to find AGNs? This is because it has been widely believed that there is a supermassive black hole in every AGN, and the mass of the black hole is related to the bulge mass of the galaxy. Therefore, in order to have a better understanding of galaxy evolution, it is very important for us to obtain a complete census on AGN activity. Actually, there are several ways to find AGNs, such as optical, UV, and soft X-ray observations. I made a small animation. This is the AGN, and observer is here. And sorry. So if there is no gas, no dust, then the UV, optical, and soft X-ray light can propagate through the space, and then we can observe it. But usually AGNs are obscured by gas and dust. In this way, then we are not able to directly observe AGNs through these observations, because these lights will be absorbed by gas and dust. So how to solve this problem? How can we observe these dust-obscured AGNs? The solution is infrared telescope. With the help of the infrared telescope, we are able to detect the re-emitted light from the dust. So here, as I mentioned, mid-infrared survey is very, very important, because by studying the thermal emission from AGNs in the mid-infrared, we can find those obscured AGNs. But in the mid-infrared wavelengths, star-forming galaxies also perform strong path features. Therefore, if we want to use mid-infrared data to try to detect AGNs, it's very important for us to separate AGNs from star-forming galaxies. And actually, there are some well-known mid-infrared surveys such as Spitzer and WISE. However, we can see in the Spitzer, IRAC, and MIPS, there is a gap in the filter, between the filter. Also in WISE, there's also gaps. This will make the AGN classification more difficult, because if the features of the source are located in these gaps, then we are not able to tell whether this is an AGN or this is a star-forming galaxy. Here I want to introduce ACARI. As Thomas-san mentioned, ACARI is an infrared space telescope with continuous light band filters in the NEP wide field. As we see this filter response, there is no gaps between. So we will not lose any AGNs by using this kind of mid-infrared data. And this is our NEP region. The gray circle is the NEP wide field. It's about 5.4 square degrees. So I want to talk about my data selection. Basically, I use the band merge catalog from Kim et al. In preparation. They cross-match the source in different wavelengths with ACARI sources. So basically, it contains Subaru, Maidanak, Flamingo, Spitzer, some infrared data, optical data, and UV data. So in total, I use 36 filters from the catalog. And there are around 92,000 ACARI sources in this catalog. And this is my data selection, because the method I use is kind of energy balance mechanism based. Therefore, I require the far infrared detection. Also, for our SPECZ sources, there is already X-ray and spectra and AGN catalog. So I compared with my SED result with the AGN catalog first, and then extended to all the samples I use in my work. So here I introduce my method. The code I use is SIGAR. SIGAR is a spectral energy distribution code derived by physically motivated modeling based on the energy balance from the UV to far infrared or even sub-millimeter. It can also provide us some physical properties of the galaxy, such as star forming rate, stellar mass, AGN contribution, and so on. So it's a kind of very good code for us to understand some physical properties of our even AGNs or SFGs. How can we find AGNs with SIGAR? In SIGAR, because there are many modules we can use, and there is one parameter in each model called AGN fraction. This means the fractional contribution of AGN emission to the infrared bolometric luminosity. That means if the AGN fraction is higher, there's high AGN activity in this source. And to avoid misunderstanding from other literatures, we use AGN contribution instead. And in my work, we set AGN contributions from 0 to 0.7. And I want to show you there are two examples of our SEDs. As we see, this is a typical star-forming galaxies. There are two bumps from stellar part and the dust part. But for AGN, there is a parallel light spectra because of the thermal emission of the AGN. Therefore, it's easy for us to tell whether this is star-forming galaxies or AGN. So here's my result. This is a relationship between redshift and total infrared luminosity. As we see, when the redshift is higher, the luminosity is also higher. And there are more sources with higher AGN contribution. It's natural because in the high redshift, we can only detect some bright sources. So we really want to know whether AGN contribution is redshift dependent or is infrared luminosity dependent. Therefore, we bin the redshift and the total infrared luminosity to see whether the contribution is redshift dependent or it's infrared luminosity dependent. And from the figures we can show, actually there is, compared with these two figures, we believe that this galaxy, a galaxy has higher redshift tends to have higher AGN contribution. But it's not clear that there is a relationship between the total infrared luminosity and AGN contribution. We also carefully compared with our SED AGNs with the X-ray and spectra AGN catalog. We check it and we define the sources with AGN contribution larger than 0.2 have high AGN activity. That means that's our AGN candidate. So we checked with the catalog and found that only 19 sources were detected by the spectroscopic and X-ray survey. But we have found 56 SED AGNs in the RSPEC samples. In total, if we include photo-Z sample, we have found 285 SED AGN candidates. And we try to compare with previous previous AGN selection called color diagram. We compare with this is the Akari AGN box, and this is the WISE AGN box. You can see that actually not all of our sources are in this AGN box, but there are still some spectra and spectroscopically and AGN, X-ray AGN are located outside the box. For WISE 2, there are still many outside the box. So this implies, that this traditional color box, because they only have two parameters, it's not very complete for us to, it's not comprehensive for us to really classify AGN. And this is other findings. We found we found 2 cases in our agent catalog, and actually they are spectroscopically confirmed. This is the agent. This is the SED of one quasar. As we see, we can see a very clear parallel like SED, and this is the HSC and Akari image. It's a point-like source, and also we get the spectra of it. There's a mission line, and finally we confirm that this is a type 1 quasar. So this is my summary. There are high possibility that there are high agent activity if the galaxy has high agent contribution. And we have found there are 285 SED agent candidates in our work. And we found that the traditional color selection criteria may miss AGNs. And agent contribution has more dependent on redshift than total infrared luminosity. And there are actually some ongoing work such as SCUBA 2 observation in the AEP wide field, as Tom-san mentioned. And one of our collaborators is doing the environmental effects on agent activities. And he will give a talk tomorrow. So maybe you are interested, you can join this session. So I stop here. Thank you very much.
Any questions and comments? No questions? Okay. So the next question. So you said like in one of the plot you say you expect that you find more AGN, more luminous AGN contribution at a higher redshift.
Yes.
Now, can you just test it by simple statistics, like because you know like what is your depth of your selection? So have you tried to test it just by simply counting the statistics? Like you assume that the AGN intrinsic luminosity or property independent of redshift, then you just do a selection cut. And then do you get the same results what you get from observation? So you say for sorry, that's probably going to be wrong with it.
You mean to understand whether this is agent contribution is really redshift dependent or not? I think maybe we still need the far infrared. We still need the high redshift data, maybe beyond 4 or something. That's why we, because we expect this. If we have the JWST data, maybe we can have more high Z sources, then we can really check if it's really redshift dependent.
Any other questions? Comments?
I'm just curious about that because I think in X-ray luminosity we can divide the agents from normal gas.
Yes.
Because for the higher luminosity to 10 to 40 or 10 to a lot than normal gas. So I'm curious just why you just fix the infrared band. Why not just try normal band and to define the agent and then use infrared later?
The reason we use infrared data is because we have more high-Z sources. If it's we only use it by X-ray, then we might lose some high-Z sources, right? Because the resolution of the X-ray is not very good, and X-ray is very money-consuming. So we try to find the efficient way to do the agent selection.
Next chance. Okay, for no further question, let's thank King Win again, and also thank all the students.